Hello and welcome to T1 Day 8 of Honors Precalculus. Today we're going to talk about the composition of functions and inverses. And a test is coming up. So here's our first problem. First, it gives us that f of x is equal to 3x squared, and it gives us that g of x is equal to the square root of 2x plus 1. We're going to evaluate each of the following and state the domain of each. First of all, in our first example, we're just adding the two together. So all we're doing here is doing 3x squared, and we're adding to it the square root of 2x plus 1. As for the domain, we have to ask ourselves, what are we not allowed to plug in here? And that's going to be limited by what's underneath the radical sign right here. And that number right there, or that quantity, 2x plus 1, needs to be greater than or equal to 0. Remember, you can take the square root of 0. So 2x has to be greater than negative 1, which means that x has to be greater than or equal to negative a half. So that right there is our domain. Subtraction of functions is very similar, except we're just subtracting. So in this case, we're going to have the first function, 3x squared, and we're subtracting the second function. Again, the only limiter is what's underneath the square root sign, so the domain will be the same. We can also, remember, write the domain as inclusive of negative a half, comma, infinity. That would be interval notation. I actually really like this. Moving on, this dot right here means multiplication, the filled in dot. I don't like using it, but you see it all over the place, so we need to make sure we understand what it means. And another way to write it is f times g of x. So in this case, we're taking our original function for f of x, which is 3x squared as given above right there, 3x squared, and we're multiplying it by g of x, which is the square root of 2x plus 1. You can leave it like that. There's nothing you can do to simplify that. You can't multiply in 3x squared inside. Again, the domain is only limited by the square root of 2x plus 1, and again, the same thing holds. 2x plus 1 must be greater than or equal to 0, so 2x has to be greater than or equal to negative 1, so x has to be greater than or equal to negative a half. So the domain, again, on this one is inclusive of a negative a half to all the way extended to the right. Division, all we're doing here is writing f of x over the square root of 2x plus 1. The difference here is that for our domain, this can't be 0 because the denominator of a fraction can't be 0. So in this case, 2x plus 1 has to be greater than a 0. So 2x has to be greater than negative 1, so x is greater than negative a half. So the domain in this case is going to be not including negative a half infinity on the interval. This is where things get fun. This open dot means function composition. So what we're saying here is that g is going to get plugged inside of f. So the way you can think about this is f of x was originally 3x squared. So instead of x, we're going to write g of x. We're going to plug g of x in right there, g of x. Remember, g of x was the square root of 2x plus 1. So all you're doing is you're plugging in g of x inside f of x. So what is that going to look like? You're literally plugging that in right there. You're going to have, so you're plugging in g of x. I'll put this in right here. You're plugging in g of x inside. So what does that mean it's going to be? 3 times, and inside of it goes the square root of 2x plus 1. But you're squaring that because that original square is part of the f. This can get cleaned up. A square of a square root is itself. So this actually equals 3 times 2x plus 1, which indeed is just 6x plus 3. What's the domain here? You have to be very, very, very careful about this because you need to look at the original function that you plugged in before you simplified it. Before you simplified it right here, this is important, you couldn't have the square root of a negative number. Again, so this has to be greater than or equal to 1. 2x plus 1 has to be greater than or equal to 0, sorry. So 2x has to be greater than or equal to negative 1. X still has to be greater than or equal to negative a half. So in this case, the domain is still this. You do the domain before you do the squaring. It's interesting. Very, very, very cool. So in this case, we're going to do it backwards. We're going to plug in f into g. We're plugging f into g. Now, g was just the square root of 2x plus 1. So what we're going to do is instead of x, we're going to replace it with f of x. Instead of x, we're going to have f of x. So it's 2 times f of x, and we're plugging in f of x for x. But we know f of x is equal to 3x squared. So we're taking this and plugging it in right there. So we know that g of f of x is going to be the square root of 2 times 3x squared plus 1. You can simplify this to be 6x squared plus 1. And now, since there's no squaring, we can look at this right here. We know that this has to be greater than or equal to 0 for this to be a valid operation underneath a square root. So we have 6x squared is greater than or equal to 1. But since this is a square, it's always positive. It's always positive. So it always has to be greater than -1, so it's always true. So the domain in this case is all real numbers, which you can write as negative infinity, infinity. So you can compose in two different directions. In this case, we plug g into f, and in this case, we plugged f into g. Next, we're going to look at inverse functions. This is really important. What they do is they undo everything that a function does. The way you can think about it is, if a function takes a to b, the inverse takes b back to a. So let's say you had f of x is equal to x plus 2, and g of x is equal to x minus 2. So those undo each other. If you plug in, let's say, f of 3 is 3 plus 2, which is 5. Well, g of 5 is 5 minus 2 is 3. Look what it did there. This turned 3 into 5, and this turned 5 back into 3. They are inverses of each other. Here's how you make note. This is the notarization of inverse, f negative 1. That does not mean 1 over f of x. That does not mean 1 over f of x. It just means the opposite function. And here's how you do it. It does it does not mean 1 over f of x. So how do you figure it out? Well, for this example right here, this is y equals 3x minus 4. The first thing you do is you just switch all of the x and y's. In this case, you just write it as x equals 3y minus 4. And now you solve for y. So you have x plus 4 is equal to 3y. So x plus 4 over 3 is equal to y. So the inverse function is this, y equals x plus 4 over 3. The first thing you do is you replace all the x's with y's and vice versa. So in this case, it's just a swap. And then you solve for y. So this right here is f, do we call it f? Yes. F inverse of x. That is f inverse right there. So we do the same process over here. Keep in mind, this means to the 1/3 power. That's one thing you can say. It's to the 1/3 power if that helps you. Cube root is to the 1/3 power. Square root is to the 1/2. So the first thing we do is the original function is y equals 2x plus 1 to the 1/3. The first thing we do is we write all the x's as y's and all the y's as x's. So we have x is equal to 2y plus 1 to the 1/3. Now we need to isolate. We need to isolate y. To isolate y, we need to cube both sides to get rid of that 1/3 power. So we end up with x cubed is equal to 2y plus 1. So x cubed minus 1 is equal to 2y. So x cubed minus 1 over 2 is equal to y. So in this case, what do we, f of x. So f inverse of x is x cubed minus 1 over 2. Kind of cool. And remember, it's not to the -1 power. This means inverse. So now we're going to find the inverse and state the domain and range of both f and f inverse. So let's do the domain first. What's the domain of this one right here, of f? Well, it's all the things except for the thing that make the denominator 0. So 2x plus 1 cannot be equal to 0. So 2x cannot be -1. So x can't be -1/2 right there. It can't be -1/2. So in this case, the domain is all real numbers except for x cannot be -1/2. So I'm going to put a pause on finding the range because there's a really cool way to find the range with the inverse. So let's find the inverse. If this is the original function right here, the first step is to replace all the x's with y's and all the y's with x's. So x is equal to y plus 3 over 2y plus 1, just like this. Now we need to isolate y. Remember, we're isolating y now. Isolate y. To isolate y, we're going to cross multiply. So we end up with y plus 3 is equal to x times 2y plus 1, like this. And now we need to get everything with y in it on the same side. So we're going to have to distribute here. We need to distribute this x in. So we end up with y plus 3 is equal to 2xy plus x. So I'm going to move this one to the other side. So it's y minus 2xy, and move that 3 over there, equals x minus 3. We're doing this because now what we can do is factor out the y's. So we have y times 1 minus 2x is equal to x minus 3. So y is equal to x minus 3 over 1 minus 2x. This right here is the inverse right here. This is, and I'll write that a little cleaner right there. This is the inverse function for f. F inverse is equal to this thing right here. The cool thing that you need to know is that the domain of the inverse is the range of the original function. The domain of the inverse is the range of the original function, which is really, really cool. So what that means is, let's do the domain here. The domain of the inverse, well, 1 minus 2x cannot be equal to 0, so 1 cannot be 2x. So 1/2 cannot be x. X can't be a half. That's the domain of the inverse, which means that this right here is the range of the function of f of x. So if we want the range of that, we can just plug it in up here. So the range of the original function is the domain of the inverse. X can't be a half. Similarly, the domain of the original function is the range of the inverse. So therefore, the range of f inverse is going to be the domain of the original function. So x can't be equal to, sorry, y, not y, it's y can't be equal to negative 1/2. So it can't be equal to negative 1/2 because that is the number that the domain can't be. So again, the domain of the function is the range of the inverse, and the domain of the inverse is the range of the function. So let's graph these and see what a function in its inverse looks like. So if we just graph f of x, this is going to be x cubed moved up 1. If you graph x cubed, and it starts here, and it looks like this S-curve when you graph it, but we need to move it up 1. So it actually starts here. You can plot some points. Here is the inverse, and you can plug in values here. So for example, plug in 2. 2 cubed plus 1 is 9. So this is actually up here. And then it's going to go down. Negative 2 is going to be down. It's going to be real down, but right around here. So it's a curve. I'm going to try to draw this nice and smooth. So this right here is, with the arrows, y equals x cubed plus 1. So we could find the inverse, or we could graph it. And here's how you can graph the inverse. To graph the inverse of a function, draw y equals x as a dotted line right here. So this is y equals x. Here's our dotted line. What you do is you reflect over y equals x. You reflect over it. You swap the x and y coordinates is what you do. So now if I graph that, what does that mean this looks like? It means that these 3 points are on the function, and it's going to be out like this, and this is what it's going to look like. It's going to be a curve that goes like this. If you were to fold the screen in half over this line, you would get those two. So that's how you can reflect. So this would be f inverse of x right here, which is pretty cool. All functions have inverses, which is really cool. All functions have inverses. All functions have inverses. A function is invertible if its inverse is a function. Now, all inverses aren't always functions, but a function is invertible if its inverse is a function. The quick way to test if something is a function, if it passes the vertical line test. So in this case, what that means is any vertical line will pass through at most one point of each, the blue and the red. If something passes through more than one vertical line anywhere, it is not a function. Another way to say invertible is that the function is 1, 2, 1. And what that means is each y value, every y value has one x value. A function is invertible if each y value has one x value. So we look at these. Are these invertible? Well, are each of the following invertible? Well, x cubed just looks like this right here. Does it pass the vertical line test? It does. Every vertical line you can draw only passes through once. And if you reflected it over, what would it look like? You would flip it over y equals x. It gets a little bit tricky to do this. You end up with something that looks like this. It also passes the vertical line test. It only passes through once. What about x squared? What does that look like? Well, x squared does look like this. It is a function, but every y value, there's more than one x value that maps to it. So for example, right here, there are two x values here and here. You can also see what happens if you try to reflect this over y equals x. If that's the origin, here's y equals x. If I were to turn this sideways, what happens? It looks like this. Does this pass the vertical line test? No, it does not pass the vertical line test. So this is not invertible. This one is not 1 to 1. And when we say not 1 to 1, we mean the black function y equals x squared. Here's the cool observation which comes with inverses and composition of functions. If f and g are inverses, meaning they're inverses of each other, they undo each other, then if you put g inside of x, you end up with x. And if you plug f inside of g, you end up with x. So up above, when we did those function compositions, we didn't end up with x, so they're not inverses one another. So look what happens here. If we wanted to verify that these are inverses, we're going to take g and we're going to plug it in for x over there. We're going to take g and we're going to plug it in for x. So what does that mean? F of g of x, that's going to be the yellow here, is going to be equal to, and that's a 2 out front, I'll keep some space for the 2 times, we plug in g of x cubed plus 5. So this is going to go right there, cube root of x minus 5 over 2. Well, when you cube a cube root, it gets rid of the cube root. So you end up with 2 times x minus 5 over 2 plus 5. Well, those 2's cancel, and you're left with x minus 5 plus 5, which is x. So that's f of g of x. So now we also need to do g of f of x, and what that means is you're taking f of x right here, and you're plugging it in right there. So what does that mean right there? It means we have the cube root of, and instead of x in there, we're writing this. What's going in there is 2x cubed plus 5. So if we write that out, you end up with the cube root of 2x cubed plus 5 minus 5 over 2, like this. So now what happens here? You end up with the cube root of, well, the 5's cancel, 2x cubed over 2. The 2's cancel, and you end up with the cube root of x cubed, which is just x. So in this case, both compositions come out to be x, so we verify that they are inverses. And just remember, you have a test coming up.